The topic of the lecture is fluids. I will discuss some properties of fluids, such as hydrostatic pressure. I will also talk about the hydraulic principle. I will explain how the hydraulic principle can be used in a device which is essentially a simple machine. And I will continue and finish with fluid flow. Fluids are simply defined as substances that flow. Liquids and gases are flowing substances, and so therefore all gases and liquids are fluids. Fluids have enormous application potential in all areas of technology and life. Fluids are used in car brake systems. The principles of fluid dynamics are used in airplane travel, sailing. Air conditioning systems involve use of fluids and circulation of fluids, and so on and so forth. So let's first discuss hydrostatic pressure. So pressure is defined as a force applied on a certain surface area. The relationship between pressure, force, and area is given with this formula, where P is the pressure, F is the force, and A is the surface area. An example of a process where force is applied over a certain surface area would be a piston in an engine cylinder. The fuel mixture enters the cylinder, it gets ignited, it expands, and so it pushes with certain force on the surface area of the piston, which makes the piston move. So pressure is applied on the piston. Now, when we talk about fluids, the way pressure is applied is specific for fluids, meaning the force acting on an object is applied from not only a certain direction, like in the example with the piston here, but from all directions inside the fluid. So this object is submerged in some fluid, and so the fluid applies force from all directions on the entire surface of the object. The force that the fluid applies is by magnitude the same from all directions. As long as the object maintains the same level inside the fluid, this force will not change. If the object moves up or down, the force will change. If the object moves up, the force will decrease. If the object moves down, the force will increase. And so, since pressure is calculated as force divided by surface area, for this object, the pressure that it's going to feel from the fluid will be equal to that force applied by the fluid divided by the entire surface area of this object. And so, because of the nature of how the force is applied by the fluid on the object, the pressure in a fluid is called hydrostatic pressure. So there is a name change because of the way the pressure is formed. Before I define the hydrostatic pressure inside a fluid, let's first talk about density of fluids. So there is two types of density that can be defined for a fluid. That would be a mass density, which is simply the ratio of the mass to the volume of the fluid. And then we also have weight density, which is the ratio of the weight of the fluid to the volume of the fluid. So the mass density is based on mass, and the weight density is based on weight, which is force. So two different things. So a typical unit for mass density is kilograms per cubic meter, and that's a metric unit. And for weight density, a typical unit is pounds per cubic foot, and this is an imperial unit. And the reason for those two different definitions is that the metric system uses mass as a quantity that enters in various types of calculations. But in the imperial system, the accepted quantity is the weight. So here in the USA, instead of mass, we always talk about weight, which is force. It's not the same thing. Okay, so I'm going to use the definition of weight density to define hydrostatic pressure. So the pressure inside of a fluid is given by this formula. The pressure is equal to the depth h inside the fluid times the weight density of the fluid. The mass density of water, so here are two specific values for the mass density and the weight density. Those specific values are for water, since it's the most common element on Earth. And we are going to do our examples today with basically water only for ease of calculations. So the mass density of water is 1,000 kilograms per cubic meter. That's a constant. And the weight density of water is 62.4 pounds per cubic foot. That is also a constant. So those two values you can include in your formula sheet for when you're doing problems on fluids during a test. As I was saying on the previous slide, the hydrostatic pressure depends on how deep this object was submerged in the fluid. As you can see in this formula here, the hydrostatic pressure depends on the depth inside the fluid. So the deeper the object is submerged in the fluid, the larger the hydrostatic pressure will be on the surface of this object. And the less deep the object is in the fluid, the smaller the hydrostatic pressure. So what would be the units for hydrostatic pressure? Well, in terms of weight density and depth, typical units would be pounds per square foot. And you guys know this as PSI. Another possible unit is pounds per square inch. Pounds per square inch is PSI, and pounds per square foot is PSF. So PSF, or pounds per square foot, and PSI, or pounds per square inch. So those are the two typical units for hydrostatic pressure, when for the calculation you would use the weight density of the fluid. Now let's do one example using the definition of hydrostatic pressure. Let's find the pressure on the bottom of a 5 feet deep water tank. So we know that the depth of the tank is 5 feet, and since the units here are imperial, that means that I will use the weight density of water in this example, which is 62.4 pounds per cubic foot, and I'm looking for the hydrostatic pressure. So I know the formula that calculates the hydrostatic pressure. That will be P is equal to H times dW. And so substituting the values, that is 5 feet times 62.4 pounds per cubic foot. And the feet cancel the third power here, so that becomes the second power. And multiplying the two values gives me 312 pounds per square foot. Let's convert this into pounds per square inch, PSI. So how do I do the conversion? Well, I know that 1 foot has 12 inches, and so therefore 1 square foot will have 144 square inches. So then 312 pounds per square foot. I will multiply by 1 square foot divided by 144 square inches. The square feet units cancel out, and what's left is 312 divided by 144 pounds per square inch. That is 2.16 pounds per square inch, or 2.16 psi. Now I want to also find out what is the force that the fluid exerts on a horizontal surface that's submerged inside the fluid, and also on the walls of the tank that contains that fluid. And so we know that force divided by unit area is equal to the hydrostatic pressure. So therefore, if I multiplied the hydrostatic pressure by the unit area of the object that's submerged in that fluid, I should get an expression for force. So for a surface that is horizontally placed inside a fluid, the total force is calculated as the surface area of that surface times the depth inside the fluid times the weight density, where the portion that is the product of the depth and the weight density is the hydrostatic pressure. Typically, that calculation is for the force that the fluid is exerting on the bottom of the tank. And so this area could be the area of the bottom of the tank. And so we have, in general, two types of shapes for a tank that contains fluid. So that would be a rectangular, or it could be also a cylindrical tank. So when you're calculating the area of a rectangular tank, that's pretty straightforward. It's just the length by the width. But when you are dealing with the cylindrical tank, the area of the bottom will be the area of a circle. So if the cylindrical tank has a radius r of the bottom, the surface area would be equal to pi r squared. Of course, I also may want to calculate the force that the fluid exerts on one of the walls or all of the walls of this tank. And then in this case, I will have to calculate the force slightly differently because of the way the fluid is exerting pressure on the walls compared to the bottom of the tank. And so it turns out that the force that is exerted on the walls, let's call this force F total wall, is equal to 1/2 the area of the wall times the depth in the fluid times the weight density. So in this case, A is the surface area of the wall in question for the container. So, for example, if we have a rectangular tank like this, I can calculate the force for each wall individually and then add them all together to get the total force for all walls. And if we are dealing with a cylindrical tank like this one here, then the area of the wall is calculated as the circumference of this circle, the base, times the height of the cylinder. The area of the wall for a cylindrical tank will be 2 times pi times the radius of the base times the height of the wall. An important principle with wide applications in technology is the hydraulic principle, also known as Pascal's principle. This is based on the fact that liquids are not compressible. For example, if you consider this, let's call it a tube or a pipe with rigid walls that cannot expand or collapse. And this tube is filled with some liquid, and it's the liquid is blocked on each side with a stopper. If I apply some force on the left stopper, the pressure inside will distribute evenly everywhere because the liquid is not compressible. And so the pressure that is applied on the other stopper on the right side will make it come off. So one more time, the hydraulic principle is based on the fact that liquids are not compressible. You can't compress a liquid. And second, that the pressure inside a liquid is distributed evenly in all directions. So the two important conditions for the hydraulic principle to work is that liquids do not compress and then the pressure is equal everywhere in the liquid. This principle does not apply for gases because gases can compress. It only applies for liquids. And so typical applications of the hydraulic principle is in all kinds of hydraulics, such as the brake system of a car, a hydraulic lift, excavators that are designed to move large amounts of large loads. So these are also operating on the hydraulic principle, and so on and so forth. Let's see how the hydraulic principle is applied in a device such as the hydraulic jack. The hydraulic jack essentially is a two-piston system which also has an enclosure in which a liquid is contained by the two pistons. And the usual liquid for the application is oil. So if I apply a certain force, let's call it effort on the small piston, that is going to generate pressure, which is equal to the effort force divided by the area of that small piston number 1. So let's call this area A1. And since the oil in the enclosure here does not compress, that pressure that's generated here by the piston is going to distribute itself evenly inside the oil, and it's going to be applied also to this large piston number 2. So piston number 2 obviously has a different surface area compared to piston number 1. And so because of that means that piston number 2 will be able to move resistance Fr, which is much larger compared to the effort force. And so the pressure that is applied on piston number 2, I can write as the ratio of the resistance to the area of that piston. So one more time, because this device operates on the hydraulic principle, the pressure generated by applying a force Fe on piston number 1 is evenly distributed inside the oil, and therefore that same pressure is applied on piston number 2, the large piston, and the pressure now can be calculated as the ratio of the resistance force, that is the force that this piston can move, divided by the area of that piston. So then, since those two pressures are the same, since the pressure everywhere inside here is the same, I can set both right-hand sides equal to each other. Let's see what we get. I get a relationship that is fairly similar to the basic equation for simple machines that I discussed in the previous lecture. We have an effort force, we have a resistance force, and then we have, instead of distances, we have the two areas of the small piston and the large piston. So I can also make the ratios of resistance force to effort force and the area of the large piston to the area of the small piston And those two ratios will be equal to the mechanical advantage of this hydraulic jack. Because at the end of the day, a hydraulic jack gives us a mechanical advantage in lifting heavy weights. So the mechanical advantage is equal to the ratio of the resistance force to the effort force, or the ratio of the area of the large piston to the area of the small piston. Finally, let's discuss fluid flow. So fluids, by definition, were substances that flow. And so therefore, when a fluid flows, I can define a flow rate for a fluid. And so the flow rate Q is defined as the speed of the flow times the cross-section area through which the fluid flows. So if I have a pipe with cross-section area A, and I have some fluid that flows through that cross-section area with speed V, then the fluid flow is calculated as the rate with which fluid flows. The flow rate is calculated as the product of the speed and the cross-sectional area. Okay, so what happens to the flow rate Q when the cross-sectional area of this pipe changes? Before I can answer this question, I also need to put some restrictions on the setup, and that those restrictions are that the walls of the pipe system do not change shape, so they cannot expand or compress. And also there are no holes in the walls from where liquid can or fluid can come out of the system. I'm going to discuss situations where the flow in here is only liquid, because for gases there is compression that can happen, and so therefore the discussion is not as accurate. So for liquids that flow in the pipe system, one more time, there is no holes in the walls cannot compress or expand. So what happens to the flow rate in those situations? Well, because liquids do not compress, that means that the pressure everywhere inside the pipe system must remain constant. Here's an example of such pipe system. We have a larger segment or section, and we have a narrower section. But the walls do not expand or collapse. There are no holes in the pipe system from where the liquid can come out. So therefore, the pressure in here must be equal to the pressure in here. The pressure must remain the same. How is that possible? The only way that can happen is if the velocity of the flow is different in those two different sections. In the wider section, the velocity of flow is small compared to the velocity of flow in the narrower section. And a visual example of this situation would be a wide river where you can see how the water flows, fairly slow, but once the river bed narrows, you notice that the water starts to flow faster. A different example would be if you're using a garden hose and the hose is completely open. The water is coming out at certain speed, but if you block half of the opening of the hose, you will notice that the speed with which the water is coming out is much higher. So these are examples of the process that I want to discuss here. So the pressure in the two sections doesn't change. The velocity of the flow changes. The cross-sectional area also is different. But it turns out that the product of cross-sectional area and velocity for each section is constant. So the flow rate doesn't change. The flow rate in the wide section is equal to the flow rate in the narrow section. And so if I write this as a relationship, that will be the speed times cross-section area in the first section here is equal to the speed times cross-section area in the second section. Now let's discuss the relationship between the flow rate in the wide section and the narrow section of the pipe system in terms of the radius of each cross-section. So we know that the product of the speed and cross-section area for each section is constant. The two products are equal to each other. The cross-section area of each section is calculated as pi r1 squared for the wide section and pi r2 squared for the narrow section. So let's substitute in the fluid flow formula. So we get V1 pi r1 squared is equal to V2 pi r2 squared. And so pi cancels out on both sides. And what we are left with is V1 is equal V1 times R1 squared is equal to V2 times R2 squared. Now you can see that since there is square dependence on the radius for each section, if I double the radius in one of the sections, that is not necessarily going to have the speed of flow in that section. And also if I shrink the radius of one of the sections 2 times, that does not mean that the speed will be 1/2 of the original speed of the fluid. That's because of these square dependencies. So here you have to be careful when you're calculating the speed of a fluid in a pipe system like that, or if you're calculating the radius. Okay, so typical units for flow rate. In the metric system, we have liters per second or liters per minute, where 1 liter is equal to 1, where 1,000 liters is equal to 1 cubic meter. And so this is in the metric system. In the imperial system, the units for flow rate would be gallons per minute or gallons per second. So in the imperial system, gallons are units that are used for liquid volume, and so are the liters, but for the metric system. So these are typical units that are used for liquid volume. This concludes the lecture on fluids, and you guys will get to practice these concepts that I discussed in the worksheet that you will do for that chapter.